Chapter 17 covers the concepts of electric current and resistance, which are two new components and new ways of talking about items in our electric circuits. To begin, we ask the question, what is electric current? And the answer, relatively simple. Electric current is just the flow of electric charge through a circuit. Now, we keep that vague, the flow of any type of charge, positive, negative. Most typically, though, in electronic devices, for instance, we have the flow of electrons. They're very small, they're not locked away in the nucleus, and they're relatively easy to move compared to most positive charges. We start this by looking at batteries because batteries are a really good source of electric energy and also a really good source of the driving mechanism that allows for the flow of that electric charge, or the current. Any battery has four components. It has a cathode, an anode, an electrolyte, and the salt bridge. The diagram on the right shows us just kind of a vague drawing of a battery and those four components. The cathode and the anode are typically the two pieces of metals which are attached to the terminals of the battery. So if you think about like a 9-volt battery, it has the two terminals on the top. One would be the cathode and one would be the anode. At the cathode, we have a chemical reaction occurring called an oxidation. And as we'll see in some examples of the actual chemistry, what happens in an oxidation reaction is that electrons are released. So there's a combination of different chemicals, which the net result is a release of two electrons, or actually any number of electrons. In the case of an alkaline battery, it's 2 electrons. Those electrons now needs some place to go. And so when you hook a battery up to a circuit, what happens is electrons freed up here are given the ability to go through your wires and through whatever devices you have hooked up to that circuit and get to the other side, which is where the anode is. And at the anode, you have a different chemical reaction occurring. It's a reduction reaction, where those electrons are being scooped up and used in the reaction. So for any battery, every electron that leaves that battery is going to be replaced by another electron coming back into the battery on the other side. So oxidation and reduction reactions occur simultaneously, which is why we call them redox reactions, reduction-oxidation reactions. A mnemonic for that is down here, this word oil rig, and the way to remember that is oxidation is loss of electrons, and reduction is gain of electrons. So again, oxidation occurring here, it's losing electrons to the circuit, and reduction occurring here, gaining electrons from the circuit. The other two components of a battery are the electrolyte and the salt bridge. The electrolyte is a combination of different free ions, which are charged atoms or molecules which are contained within the container of the battery. They are involved as byproducts or reactants in the chemical reactions occurring at the cathode and the anode. Typically, for a battery which is going to be efficient in sustaining itself for a long period of time, whatever types of byproducts you get from the reaction occurring at your cathode are going to be kind of facilitating the reaction on the other side, which necessitates the fourth component of a battery, which is a salt bridge. And what this does is it allows the flow of ions, and therefore it allows the continued use of that battery because as this side is producing ions, for instance, those ions are being utilized in the reaction occurring on the other side, and they're able to cross through the two compartments of the battery. What is not able to happen is electrons cannot simply pass through the battery. If that were the case, then your battery would kind of just sit there and use up its charge all on its own. So a salt bridge is kind of allowing certain components to cross, but not just allowing the battery to just sit there and kind of go through its charge. An example of an alkaline battery's chemical equations are listed here. We can see that on the one side we have zinc being oxidized, and that's the release of these two electrons. On the other side, we have manganese dioxide receiving these two electrons. And so these electrons were sent out into your circuit. These two electrons were received from your circuit. And in the end, you end up with all these oxidized metals where, because of the oxidation and because of the subsequent reduction, these two components are kind of being used up. And when your battery finally dies is when these two things kind of get used up. Now in the case of rechargeable batteries and things like that, then you can kind of get this shift back and forth of your chemical reactants and the products. But in the case of a typical alkaline battery, let's say, you're not able to reverse that so fully, and so your battery eventually dies, and then you have to get new ones. In the case of an alkaline battery, potassium hydroxide is what's serving as the electrolyte, which is primarily what this precipitate is that comes out of the battery in the case of a leaking battery. So in the case of a malfunction occurring within the battery, what's most typically happening is it's causing a reaction to occur in a way that's not really supposed to. And usually this happens if let's say you have like old batteries in a calculator and then you put some fresh ones in, and so you get kind of a mismatch of different voltages, and certain batteries trying to encourage other batteries to have chemical processes occur inside of them that they don't really want because of the voltage that's pushing on them. And in any case, it can cause a precipitate to form, and they can burst out of the battery because as this solid forms, it creates kind of a pressure that the battery can't withstand. Anyway, the whole point of that is don't eat it. It's nasty stuff, but not overly harmful to your electronics as long as it gets cleaned out. And that's why just good practice of replacing batteries. If you have a calculator, let's say that takes 4 AAA batteries, if the calculator dies, don't just find the one battery that's completely dead and replace that one. Just replace all 4 and keep 4 of the same type of battery, and that's going to minimize the chance for any kind of weird electrical or chemical things from happening. When we talk about batteries, it's important to bring up the idea of electromotive force. Sometimes referred to as the EMF, or represented here by this fancy epsilon. What the electromotive force is exactly what the name implies. It is the force which causes the motion of really the electrons. And so thinking about a battery and the voltage that it supplies, electromotive force is in effect another way of referring to the voltage that's established by a battery. And it's that driving mechanism that's going to push those electrons through the circuit. So a battery is capable of encouraging electrons to go from the negative terminal to the positive terminal through your circuit. Even if your circuit has a whole bunch of components that the electrons might have to kind of, in a way, fight their way through, the voltage and the electromotive force established by the battery is that encouragement for that to happen. And it's all really about the electrons being able to get to a lower state of electrical potential energy, which we had previously discussed. Some things about batteries. If we hook batteries up in series, what you'll find is that the voltages will add. And so this would be one way in which if you had a, let's say, light bulb and you had a number of batteries, if you hook them up in series, you're going to end up getting a much brighter result from your light bulb. And the reason for that is because, again, the voltages will work together. Because in this case, all 3 of these batteries are pushing together in the same direction. This is why in calculators and other devices you get a number of batteries adding together. And so in the case of a Texas Instruments graphical calculator, if you look inside the battery case there, you'll see 4 AAA batteries. Those are all 1.5 volt batteries. And when they're arranged as they are in a calculator, they are in series, and therefore they are contributing 6 volts. So your calculator actually runs off of 6 volts, but it gets that from 4 1.5 volt batteries, which is a good multiplier because it's a small number, and so you can kind of get different combinations of different numbers of batteries in order to get kind of the right voltage for any type of small handheld device. That's why some things only need 1 or 2 or 3 or 4 batteries. When you hook them up in parallel, it's a little bit different. As we've seen in the past, pretty much anything that you hook up in parallel is going to have the same voltage on either side of the circuit. In the case of hooking up batteries in parallel, it's the same case. The voltages will be the same. Assuming you had 3 batteries of equal voltage, you'll have the same voltage applied across your circuit. However, now you're kind of sharing the load between 3 different batteries. And so as electrons are flowing through this light bulb, they're able to come from any of these 3. Now, there's 2 ways of thinking about this. Either you could get a much larger total current that you're pulling from this because you have 3 batteries able to contribute to the current, or you could think of it as you could end up with kind kind of 3 times the length of duration to the operation of this. So if you hook up a light attached to a whole bunch of batteries in parallel, you can actually get much longer use out of that, since again, the load is kind of being shared by the different batteries. But the voltage will be, again, the same. So putting them in series gives you the increased voltage. Putting them in parallel is going to give you just the same voltage that they started with. We have some different symbols, which we've already covered. We know the batteries are represented by the shorter line and then the longer line, the shorter line being our negative terminal, the longer being our positive. Capacitor we've seen, simply wires are represented by lines. And then really the new thing that we're focusing on here is this idea of a resistor. We're going to talk about resistors in just a few moments. When we look at current through a wire, it's important to understand that it's not just a simple line of electrons flowing just all together in this nice orderly fashion through the circuit. It's easy for us to fall into the trap of thinking about it that way, just because we are imagining electrons moving from one side of the battery through the circuit to the other side of the battery. And while in a grand sense that is what's happening, if you really zoomed in on it, inside of your wire you have much more chaotic motion. We have to remember electrons are super, 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 super tiny, and they're also really susceptible to acting based on their proximity to other electrons. 2 negative electrons sitting next to each other really don't like that, and they're going to repel each other. And therefore, when you have electrons going into a circuit, you have them bouncing kind of all over the place, back and forth, up and down, left and right, away from each other. But in general, when you apply a voltage, you're going to get what's called a drift velocity, which is the general progression of electrons through your circuit. And it's much slower than an electron can actually travel, but for every electron that's put into the circuit, on the other end of the circuit, an electron's coming back out into the battery. So it does progress forward. It's just in a little bit more of a chaotic sense than what we might have imagined. To define current, we get a very simple equation. First off, current is represented by the variable I, so this is my current, and it is equal to charge, Q, per second. So it's charge over time. Now if we think back to what I had said current was, electric current is the flow of electric charge. So current being charge per second is in effect saying that current is kind of the velocity of electricity. It's how quickly you can deliver a certain amount of charge. And since electrons are the carriers of charge, another way of thinking about current is basically the number of electrons delivered per second. But you'd have to multiply it by the charge of an electron. In any case, when we look at this, there's 2 ways of thinking about the units for current. It's coulombs per second, which is charge per second, or we call that the ampere, represented by the variable A. Often we will shorten that to amps. The next major concept which we need to introduce in order to fully understand what's going on with circuits is resistance. And resistance is exactly like the name implies. It is that which resists the motion and the current through a wire. So when we think of a resistor, that's any device that you plug in that's going to in some way slow down the electrons that are passing through that wire. And we'll see why that's something that's worth knowing in just a moment. But to calculate resistance, it's equal to the voltage of the circuit divided by the speed of the electrons through it, the current. So voltage divided by current, or volts per amp, and that gives you a unit which we call the ohm, and that's represented by omega. So somewhat logical there. And that's resistance. So, like I said, helpful to think about resistance as just the resistance of motion, preventing that current from moving. And so if we think about a circuit that has no resistance, we think, well, full speed ahead. And so resistance is bad? No. Actually, resistance is the entire point of all of this. Resistance, yes, slows down electrons. But that's kind of the whole point of an electric circuit. If I just wanted to get electrons from one terminal of my battery to the other, then I would just attach a wire and I would sit there and know that my battery is dying. but that doesn't actually do anything for me. So the whole point of circuits is that we're plugging things into them, such as light bulbs or different electrical components inside of computers or whatever it is, and you're getting some sort of actual functional use out of that. So when I plug, let's say, a light bulb into a circuit, I have a wire from my battery to the light bulb and then another wire back to my battery. And electrons are moving through that light bulb, and as they do so, they are experiencing resistance and slowing down. And it's that slowing down that's actually giving us the functionality here, because an electron is a moving particle. It has mass, it is in motion, and therefore anything with mass that's moving has kinetic energy. And as that electron is slowed down, we're effectively taking that kinetic energy and we're mooching away some of it. And when we do that, we can turn that energy into other types of energy. In the case of a light bulb, it's running energy through a filament, which heats up, and in the case of tungsten, when it gets really hot, it starts emitting photons, which is light. And so we get this functionality out of it. And this is really the case for all electric circuits, and any device that's plugged into an electric circuit or an electric outlet in your house is finding a way to take the energy of those electrons and turn it into some other type of functional thing. So resistance being bad? No, not at all. Resistance is, again, the whole point of all of this. Resistance is, like I said, capturing energy from electrons and letting us do stuff with it. And that is the official physics terminology, stuff and things. Resistance is calculable from the equation R equals V over I, as we previously mentioned. And as such, if we map this out, we can see that as voltage increases, we get a linear increase in current. And this is true for any type of material that we consider to be ohmic. So an ohmic material is one where as you increase the voltage across it, the current will linearly increase along with it. And therefore, this equation up here and this rewriting of that same equation. Okay, so again, this is not new down here. It's the same equation, just rearranged. But for an ohmic material, these two things are true. For a resistor that is not ohmic, or is a non-ohmic resistor, what happens is, as you increase the voltage, the increase in current might not quite be linear, and so you might end up with something more like this, where you get to a point where as you're adding more and more voltage, you don't keep getting more and more current. There's a number of reasons why this can happen. For instance, in the case of light bulbs, they're typically non-ohmic resistors, and the big part of that is that as you increase the voltage and you get this current through it, you get this change in temperature. And the change in temperature can actually have an effect on the speed of the electrons through it, because that thermal energy contributes to that chaotic motion of the electrons. And if you get too much of that, it can really hinder the ability of the electrons to move quickly through your wire, therefore not allowing you to get that nice increase in your current that you might have expected. And instead you get something much more like this, where your current kind of stops increasing at the same rate. One other component which is very important here is power. And power is something that we've previously talked about. Power is work over time, and the unit for it would be joules per second or watts, as we've previously seen it from our work and energy chapter. When we equate power to electric circuits, we see that power is actually equivalent to the current running through a resistor multiplied by the voltage across it. And in this way, we can actually find how much power is being output by something like a light bulb or a resistor in a circuit. And we can then find out, okay, well, what's the wattage on that, or how many joules per second are actually being used. That's really important when we talk about kind of the efficiency of different items. And so in this case here, we're looking at a current of about 6 amps running through this resistor of 2 ohms. And if I was looking for the power of this, again, looking at 6 amps, which is 6 coulombs per second, multiplied by 12 volts. And another way of thinking about voltage is joules per coulomb, as we've seen from previous equations. And so if I multiply that, I get 72 joules per second, or 72 watts for this resistor. When we look at kind of energy ratings on different devices, this is the same stuff again that we looked at back in chapter 5. But here we can see that the wattage of this, 18 watts for this video cassette recorder, and that tells you a little bit about just how much power is actually being used. You'll notice some other information here on the back. We have 120 volts that this is rated for, and 300 milliamps. So again, as we're introducing new things like electric current, electric resistance, voltage, and all this stuff, you can find this stuff in the real world. I'm not just making it up here, and it very much is applicable to any type of device that you're going to plug into your wall or charge up and then use on the go. They all have these ratings for these different electrical components and how they hook up to circuits and what kind of power they use and what type of voltage they need to be hooked up to and things like that. So getting a better understanding of this stuff really does help with understanding how do all these things work, how do these things plug in, and what do they really require in order to work properly. Looking at just the power usage of some different devices inside the home. First off, some general electrical devices. A coffee maker is about 1600 watts. A blender about 800 watts. A microwave about 900 watts. It might be surprising to think of a coffee maker as being so high, but you have to remember any type of device that's really just generating heat is doing so by offering up a whole lot of resistance and therefore creating kind of a huge power suck because it's trying to mooch as much energy from those electrons as it can in order to heat up. And so that's why you get to like stoves, coffee makers, let's see, hair dryers, pretty high wattage, water heater, very high. It's a lot of power usage for those types of devices. We previously talked about all this as well, and basically just showing you again the idea that in this kind of energy conscious world that we live in these days, these things are important to understanding kind of how much power are you using when you plug in these devices to your outlets. This diagram right here is something which all of you should have or will soon receive, which is called an ohmic wheel, and it is a really handy way for us to solve for these 4 different variables. We have power, voltage, current, and resistance. And the way this works is if I'm looking at, let's say, power here, so power is equal to current times voltage, power is equal to current squared times resistance, and power is equal to voltage squared divided by resistance. Same thing with voltage over here. It's equal to these 3. Resistance is equal to these 3, and current is equal to these. What this allows us to do is solve for any of the 4 variables by only needing 2 of the others. And the reason why that's possible is just because these things are so intertwined in how they're defined and what they actually represent that, again, you only need 2 pieces of the puzzle in order to really get the whole rest of it. So a helpful thing for us for sure. And that wraps up Chapter 17.